Okay, let's talk about something called the power set. So let A be a set. The power set of A is, well, it's the set of all subsets of A. And the notation we use for this is a kind of curly P of A. Okay. So if I write this in set builder notation, P of A is equal to the set of all B such that B is a subset of A. Okay. If the meaning of this isn't very clear to you, then you should probably get more practice with this set builder notation. So the right way to read this is it's the set of all B, so all mathematical objects, of any type B, which have the property, so such that this property holds, that B subset A is true. So in other words, it's the set of all subsets of A, right? So it's the set of all B with the such that this evaluates to true. B subset A is true, right? Is this definition kind of clear or kind of confusing? If it's confusing, then maybe it becomes clear if we do an example. Or let's do lots of examples. So can anyone tell me what is the power set of the set containing the number 1? Yep. And this is maybe this is an issue a lot of people are having. So there's a very big difference between an element and a subset. So if suppose A is like the set 1. So 1 is an element of A, right? That's true. But if I write subset, that's false because, so 1 is not a subset of A because this only makes sense for sets because so 1 is not a set. So it's not going to be equal to A. Yep. Yeah. So the power set of A will contain sets that contain elements of A, but the power set might not contain any elements of A. It might become clear after a few examples, and yeah, well, hopefully that'll kind of answer your question. Does anyone have any ideas on this? Yeah. Yeah, perfect. Right, because to check that this is correct, what do you have to check? You have to check that, okay, this is a subset, and the empty set is a subset, because the empty set's a subset of everything, right? Every set has the empty set as a subset, and there are no other subsets. Of the set containing 1. So if the power set contains it's the set of all subsets of the set containing 1, these are the elements. It's that's a subset, and that's a subset, and there aren't any other subsets. Right? Is that clear? Kind of. What if we do the power set of 1, 2? So it's a set of something. So you're always going to have the empty set, right? The empty set is a subset of everything. For every set. So empty set is a subset of A for every set A. You're also going to have the whole set, right? So A is a subset of A for every set A. So I can also list the element 1, 2 like this. Which ones am I missing? Yep. Exactly, yeah. And note that, like, and this is an important distinction to make that I think a lot of people are struggling with. I think everybody struggles with when they first see sets. But there's a difference between this and the number 1, right? So the set containing 1 is not the same as the number 1. Right? This is like a box containing 1. This is just a 1. A box containing 1 is not the same thing as the number 1. And also, this is not the same either. So this is different from both of, because this is like a box inside of a box with a 1 inside of it. It's like these, Russian dolls, you got one inside of the other, It's got that kind of thing. Is this example, this okay? So does this kind of clarify your?
Like subset on all the sets.
I'm not sure I catch what you mean. Yeah. So do you just mean like if I have this, and is this equal to this, or? No. So these are definitely not equal, because what does it mean to be equal? It means everything in this set. So I'll write this to be clear. This is not equal. Equal would mean everything here is in here and everything here is in here. Now, it looks like, if I look at the number 1, it looks like it's here, but it's not, because 1 is not the same as the set containing 1. So even though it looks like 1 appears in this list, the thing that really appears in this list is 1 inside of a set, which is not the same as 1. So indeed, like this is, these things are totally different. In particular, the power set has 4 elements, 4 different elements. This only has 2 elements. They can't really be the same, right? Even though it looks like there's redundancy here, but there isn't, because the elements are empty set, set containing 1, 2, 1, and 2. There's no actual repetition here, because these are all distinct objects. I don't know if that makes things clear or even more confusing, but I would say this is an element of this set. So, 1, 2 is an element of this set, but it's definitely not equal to it, right? Because 1, 2 is right here. It's an element. Here's a slightly weird one. What if I just take power set of the empty set? Yeah. Oh, yeah. Yeah. But we have to be careful that it is the set containing the empty set, which is, we have to be, this is something that trips people up a lot. So it's not the same as just the empty set. It's kind of like saying, the empty set is like a box containing nothing, right? It's a set that has nothing in it. And this is like a box containing a box containing nothing. Those are different things. Yep. That's a very good question. So that's something, that's something I was going to ask you later, but or like ask the class later. But that's a good guess. So that it is true. Yeah, it is true. It is. The kind of pattern here is that it goes by the powers of 2. So, well, okay, maybe I'll prove that in a minute, but let's do a weird example, okay? Maybe all these examples feel weird to you, but let's do an example that might make our heads hurt. Power set of the set that contains the empty set and the set containing the empty set. Okay. Can anyone give me some elements? Yep. So this one? Yep. That'll be there because if you check, this thing is a subset of this set. because the only element of this set is an element of this set. So that's good. Yeah. Yep.
The empty set.
That's always a safe bet, right? You can always, if you're stuck and you want to write something, you can always write the empty set, because empty set is a subset of everything. There's another one as well, which is a subset of everything. Yeah.
The set containing the set of the empty set.
Yeah. This is kind of the weirdest one. Yeah. And then one more. Yeah.
Set of
Exactly. So you can take like the whole original set. Oops. And this follows the pattern that you mentioned before, right? There's 2 elements here. There's 4 elements here. 2 to the 2 is 4, right? Okay. You do have to be a bit careful with this, though, right? If I say, what's the power set of 1, 1, 2, you know, you got to remember, sets don't count repetition. Exactly. Yeah. So don't get tricked into like taking the set 1, 1 and all that. Just, you know, this is the same as if I just had 1, 2. I mean, actually, it wouldn't be wrong if you wrote like 1, 1 but yeah. Okay. That's just because this set is equal to that set. Okay, so are there any questions about this power set stuff? Okay. Sets of sets always mess everybody up. I think my only suggestion is, I don't know, practice, review it. Yeah, I don't know. Well, let's prove this this theorem. So that if A has size n, then the power set of A has size 2 to the power n. There's a really good way of thinking of this. So let's think of the elements of A as being n people, okay? Okay, so imagine I'm having a party, okay? So maybe you are the n people, right? So I can go to each of you and say, like, do you want to come to my party? Okay. Do you want to come to my party? Sure, okay. Do you want to come to my party? Okay, yeah. Do you want to come to my party? Ooh. So far, I mean, my party's very popular. You're going to be left out, you know. Right, so you can go, imagine you kind of go through these n people, and every single one of them individually you ask a question, like, do you want to come to the party? Or, for example, do you want to be part of the subset? Because you can think of the people who say yes to coming to the party, that makes a subset of this room, right? And if somebody changes their answer from yes to no, or from no to yes, that's going to give you a different subset. So basically, the answers to the question determine the subset, right? So you can individually imagine you ask each element of A, do you want to be part of the subset, or do you want to come to the party? So selecting a subset of A is the same. So maybe I'm going to already drop this people analogy, and talk about subsets, but as kind of, you know, it's the same as asking each element whether it wants to be part or wants to be in the subset, right? And then everybody who says yes gets put in the subset, and everyone who says no doesn't get put in the subset, right? And then you have to think, okay, how many possible combinations of answers could there be, right? Each person has two choices, yes or no. So if the first person has two choices, you can think of it like flipping coins, right? I've got heads or tails, yes or no. How many possibilities are there? There's two for the first person, and then when you have two for the second person as well, that makes 4 combinations overall. 2 for the third person, that makes 8, 16, 32, it just multiplies by 2. So each person, so maybe element, I'm switching between people and elements, but let's say element has 2 choices, yes or no. So the total number of combination, the total of, I guess combinations of answers, or is, so 2 for the first person times 2 for the second person times 2, so like n times, 2 times 2 times 2, with n factors here, which is 2 to the n, okay? And the key is that choosing a subset is the same as asking this question to everybody, right? So picking a subset of this room is the same as asking you if you want to come to my party. Not everybody does, right? And that's the same as picking a subset. So including, for example, the empty set, right? So if my party is going to be really boring, everybody says no, that gives me the empty set. If everybody says yes, that gives me all of A, and so on. Is that clear? Any questions about that? Okay. Well, here's something which is related to that. Do you remember these Venn diagram things? Right? Well, okay, so the simplest, pretty much the simplest one, right? You take A and B, you draw 2 circles, right? And this breaks the whole kind of universe into 4 regions, 1, 2, 3, and you have to remember the outside as well. So this is the stuff in the universe that's not in A and B, or B. So here's a question. If I take a Venn diagram with K, or let's say N sets, how many regions does that break the universe into? So here with 2 sets, it breaks my universe into 4 regions. With 3 sets, what do we get? 3, 4, 5, 6, 7, 8. Looks like a similar pattern, right? Yeah, exactly, yeah. And this is for kind of a similar reason. But yeah, basically, okay, first of all, I can't draw up a Venn. One thing about Venn diagrams is when you get more than 3 sets, I don't know how to draw that, but in theory, a Venn diagram with n sets has 2 to the n regions. Okay, and here's like a reason why. So okay, so for two sets, let's say A and B, okay, one of my regions is this one. So which region is it on this picture? A intersect B, 2, yeah. So A intersect B is region 2, or maybe just write 2 with a circle. Another region is like, what about A complement intersect B? So that's the stuff that's not in A, but it is in B, probably, yeah. So that should be 3, right? Because 3 is the stuff which is in B, but not in A. And then these are my other 2 regions. So this is going to be region 1, and this is going to be region 4, because this is the stuff that's not in A and also not in B. So it's the outside of everything. So in some sense, like the way you get all the regions of a Venn diagram is by taking like A intersect B and choosing some locations to put complements on, right? So we have no complements. This is kind of like the sets where I put the complement is like the empty set. I mean, you don't put any complements. You put a complement here or both. And for 3 sets, for example, if I've got A, B, C, if I take, for example, A complement intersect B complement intersect C, that's going to give me region 7, for example. And every combination of putting complements in different places will give me a different region. Okay? So the number of regions is going to be equal to the number of subsets, like, of the sets I have. First of all, let's practice some of that subset counting stuff, and then let's try a variation of that, which will lead us to something called inclusion-exclusion. So just to recall, so let A be a set of cardinality n. We remember, what does cardinality mean? You know, it means that the size of A is n, right? Cardinality is the size of a set. Does anyone remember how many subsets does A have? Yeah, exactly. Yeah. Right, and the kind of concept there was choosing a subset of A is the same thing as going through the elements one by one and asking them, do you want to be in the subset? And if they say yes, you put them in the subset. If they say no, then you don't. And the number of subsets is the same as the number of different combinations of answers that the elements could give you. Okay, so 2 to the n. Let's look at some variations of that. So how many, and this is going to test some of your vocabulary, how many proper subsets of A are there? Yeah, it seems reasonable. So how come? Exactly, yeah. So if you know the definition of proper subset, then this is not too hard, right? But remember, so just to, in case somebody doesn't remember this vocabulary, a proper subset is well, this is the symbol, right? This means B is a proper subset of A, which means B is a subset of A, and B is not equal to A. Okay. And in particular, this is not the same as saying it's not a subset or something, right? The cross is, you should think of this as the cross is through the equal sign. So it's just saying it is a subset, and you know, the equal, like, is crossed out, so it's not equal, but it's a subset. So yeah, exactly, this argument makes total sense. Take all the subsets except for A itself. Yep. Yes, unless A itself is the empty set. That's one. There's always these sneaky little things, but yeah, if A is, if this n, if the size of A is at least 1, then the empty set is a proper subset because it's a subset of A. The empty set's a subset of everything. So it's a subset of A and it's not equal to A. But if A is the empty set, it's not a proper subset. And actually that checks out with this formula, because if n is 0, this gives you 2 to the 0, which is 1, minus 1 is 0. So the empty set has no proper subsets. It has 0 of them. Okay, so how about, what other variations do I have? Okay, so what if I have some element of A so let X be an element of A. How many subsets contain, or let's say don't contain, sorry, X. Yep, exactly. So what's a like a justification for that? Yep, that'll work, yeah. So it's kind of like here we're kind of asking each element the question, do you want to be in the set or not? Except we already know the answer for X. X already said no, it's not going to be in the subset. So it's kind of like you have one fewer question to ask. So there's one fewer 2 in the product. You can also, another kind of cheap way of doing this is just say, oh, well, it should be equal to the number of subsets of A minus X, right? Because if you have a subset of A that doesn't include X, it's a subset of A minus X. The size of A minus X is n minus 1. So that's two different ways to look at the same thing, right? Because, you know, the size of A, if A has size n, then this is going to have size n minus 1. Okay. Another question, how many do contain X? So we looked at the ones that don't contain it. How many do contain it? Well, actually, maybe the answer that was given for the last question is a good way of solving this, right? It's kind of like you're going through all the elements and asking them if they want to be in the set. So before we knew that the answer for X is no. Now we know that the answer is yes, but that doesn't make any difference, right? You still have 2 to the n minus 1 choices for the other elements. So it should be 2 to the n minus 1. There's always millions of ways you can do these things. Like, you could also say, okay, well, it's 2 to the n minus 2 to the n minus 1, because this is all the subsets. If I take all the subsets and I subtract the ones that don't contain X, and if you kind of think about this, that's actually 2 to the n minus 1. So we get the same answer multiple different ways. Okay. So this is maybe to do this in more than one step. So 2 to the n is 2 times 2 to the n minus 1, and then minus 2 to the n minus 1, which is just 2 to the n minus 1. Okay. Any questions about that? So just to be clear here, I'm giving 2 different proofs of the same thing, right? We got the same answer, so it's not really different. Okay. Let's try one which is not quite so clear. At least I think it's a little bit of a step up from this. So now let's say that X and Y are both elements of A where they're not the same element, right? So 2 different elements. How many subsets of A contain at least one of X or Y? So it could contain X, it could contain Y, it could contain both. So before giving you the right answer, or actually, does anyone have an idea first? Okay, before giving you the right answer, let me give you the wrong answer, okay? So I don't know if this is a good idea but let me just highlight, this is the wrong answer, okay? Do not think in the future that this is the right answer. But you could think, oh, well, you could just say, oh, how many contain X? Well, there's 2 to the n minus 1 that contain X. And there's 2 to the n minus 1 that contain Y. So just add them up, right? Because by symmetry, yeah, if there's 2 to the n minus 1 that contain X, there's also 2 to the n minus 1 that contain Y. And this is actually, if you think about it, going to give you 2 to the n, which is all of the subsets. I mean, there's 2 to the n subsets. Why? Does anyone see why this is wrong? Yeah, exactly. Yeah, that's perfect. So, right, because, yeah, if you think about a set, imagine a set that contains both X and Y. When I do this count, I count that set. So, for example, like the set XY, for example. This set gets counted in this expression, but then it gets counted again in this expression. So it gets double counted. So this is going to be too big. Like this is going to be bigger than the right number. So then can anyone see how to fix it? Yeah. Ooh, that would be a good way to do it. That's an alternative method of doing it. Yeah. So you could take 2 to the n minus the number that don't contain x and also don't contain y, which is exactly. That's always going to work. That's going to work as well. So these are the ones that don't contain x and don't contain y. So this is going to give the right answer. It turns out this gives you 3/4 2 to the n. If you do the math, because 2 to the n minus 2 is equal to 1/4 2 to the n. Oops. Anyway, that's a great way of doing it. How would I? But let's suppose we try to do it this way. How would I fix this proof? Or how would I fix this calculation? So here I counted the things that contain x. Here I counted the things that contain y. Sets that contain both got double counted. But what you could do is just subtract the ones that got double counted, and then everything should get counted just once. So another way of doing, so this is one way of doing it, and this is another way of doing it. So this is counting the ones, this is subtracting the ones that contain both of x and y. And again, this gives you 2 to the n minus 2 to the n minus 2, which is 3/4 2 to the n. By the way, if you're doing something on a test or something, like this is a perfectly fine final answer. I'm just writing it this, there's no good reason to write it this way, but anyway. Okay, well, this illustrates a few things. One thing it illustrates is that there's more than one way to count pretty much anything. But it also illustrates this concept, which is called the inclusion-exclusion principle, or principle of inclusion-exclusion. This idea that sometimes what you can do is like count one thing, count another thing, and then look at what you've double counted and subtract that. And that's a general method for counting statements which have an or in it. So the important thing here is there's an or. Okay, let me give you the statement of the of inclusion-exclusion. So this is the principle of inclusion-exclusion, but only in the case of two sets. So we'll see other versions of this for 3 sets, and maybe I'll talk about more sets. But this is just for the case of 2 sets. So let A and B be finite sets. Then the size of the union of A and B is equal to the size of A plus the size of B minus the size of A intersect B. This is kind of what we were doing in this answer over there for that question. So if you think about A union B, you can think of that as all the elements that satisfy one condition or another. The condition being that it's in A or it's in B. So this is like the things which are in A or in B. And a way to count that is to say, okay, let's count everything that's in A, let's count everything that's in B, but then you realize, oh, something got double counted. It's the things that are in both, and you subtract that, and then everything gets counted once. That's actually basically the whole proof, right? So you can kind of see this with a Venn diagram. So I'll kind of draw a Venn diagram, but also kind of properly prove this as well. But let's say, so okay, if I take the expression A union B, cardinality of A union B, so this counts each element of, okay, so if I let's draw a Venn diagram, right? Just briefly. So So when I compute A union B, or the cardinality of A union B, everything in this segment gets counted once, this segment gets counted once, and everything in the universe outside of A union B gets counted 0 times. So each element of A minus B gets counted once, A intersect B once, B minus A once, and the rest of the universe 0 times. Is it clear what I mean by gets counted by, right? Like, you know, this union should count every element here, here, here once, and then everything here gets counted 0 times. And now I want to say, okay, this side of the equality counts the same thing. And if two expressions count the same thing, or if they count every element the same number of times, then they must be equal. So maybe I'll just first look at our A plus B. So A plus B, so cardinality of A plus cardinality of B counts each element of A minus B once. So if you think about, again, think about the Venn diagram. When I count A, I count the things in B. You see everything in A minus B gets counted once. B minus A gets counted, well, let's do the intersection. A intersect B gets counted twice because it gets counted in both terms. B minus A gets counted, everything there gets counted once, and the rest of the universe. Okay. So therefore, if we subtract A intersect B, then everything, you know, well, let's say it gets counted the correct number of times. Okay, that's maybe not the most well-explained proof, but hopefully the concept is clear, right? Right, so if when I, you know, at this point I'm counting these things once, twice, once, and 0 times. If I then subtract the size of the intersection, that'll cause each of these to be counted only once because I subtract 1. So now everything gets counted once except for the rest of the universe outside of A and B. Any questions about that? Okay, maybe let's do an example. So suppose you've got there's 200 language students. You've got 50 of them speak Japanese. You've got 45 of them that speak Korean. You have 20 that speak both. And then the question is, how many speak neither Japanese nor Korean? So how many don't speak Japanese and also don't speak Korean? Okay, so imagine like this is like the whole language department or something. You know, not everybody speaks Japanese or Korean in the language department. You have 50 speak Japanese, 45 speak Korean, 20 speak both. How many don't speak either? Any thoughts about this? Yeah? Yeah. So that's going to tell you how many speak one or the other, and that's like most of the answer. So, but yeah, and then we want to subtract that from 200. Yeah, totally. Oh yeah, probably. I don't know off the top of my head. I can't do this math in my head, but yeah. Well, so for a solution, I mean, let's first compute. So let's let J be the set of Japanese speakers. K be the set of Korean speakers, you know, in the set of language students. Let's say U is the set of all language students. Right? So, and U is our universe. So what this is asking us to compute, okay. Well, okay, maybe first of all, let's just compute how big the union is. So J union K, so as was suggested, this is, well, it's the size of J plus the size of K minus the size of J intersect K, which is 50 plus 45 minus 20, which I think is 75. But that's not quite what the question was asking. So this is so 75 speak at least one of Japanese or Korean. I'll just write J or K. But that's not quite what we're asking for. We're asking for the ones who don't speak those languages. But then you just subtract that from the universe. So 200 minus 75, which is 125, don't speak either of the languages. So that would be our final answer. Okay. So sorry for our very first practice with this. I threw a little bit of a curveball, right, by asking the ones that don't speak those languages. But it's like not that much of a step, right? You just take the ones that do speak at least one of the languages and subtract that from the whole thing. Okay. So in other words, like this is asking, I mean, really, this is the size of the complement of J union K, right? Which should be the size of the universe minus J union K. Right. So the key thing was to compute the size of J union K, but you have to subtract that from the universe. Okay. Any questions about that? Has anyone seen inclusion-exclusion before, or is this new to people? So if you have seen it, put your hand up. Okay. So it's not that, for most people, it's probably it seems to be the first time. Okay, any questions about this example? Okay. Well, let's try to work out. So this is just inclusion-exclusion for two sets. And it's pretty easy to use, right? Take the size of the first set, size of the second set, subtract the intersection. You basically just need to remember that, you know. Basically, the only places you can get stuck here is A, not remembering the formula, or B, not reading the question fully. But otherwise, you should be okay. Okay, so What about 3 sets? Maybe I'll erase this as well. So imagine I'm trying to compute the size of the union of A, B, and C. And suppose I want to do this by starting like in the same way we did before, just by taking, I just start by saying, oh, how big is A, how big is B, how big is C? And I add those up. Okay, this is not going to be correct because things which are in multiple sets are being counted more than once, right? But we have to think about, how many times are they counted? So for example, so here's my Venn diagram, right? This is A intersect B intersect C. How many times is something there counted? Yeah, so I see some fingers, but anyone want to volunteer? Yeah, 3 times. So what I'm saying, anything that's here gets counted 3 times because if X is an element of the intersection of A, B, and C, X gets counted when I compute that cardinality, it gets counted here, and then it gets counted here again. It gets counted 3 times. What about something like here? So this is the stuff that's in A and B, but not in C, twice, right? Because it gets counted when we compute the size of A and the size of B, but it doesn't get counted when we compute the size of C. And then similarly, these things get counted twice. This stuff gets counted only once. So we've got like big problems here, right? I mean, we've counted this stuff the wrong number, like totally the wrong number of times. So we have to fix it. So here's a suggested way of fixing it. What if I subtract the intersections? This is kind of what we did last time, right? And that worked, so maybe it'll work again. Okay, so that's kind of a random thing to do, but let's see what happens. So after I do this, how many times is something here being counted? Yeah, I see at least 1 finger, which is getting the right answer. Or I guess I said finger, which suggests that the answer is 1. And indeed, it is 1, right? Because previously it was counted twice, and then I subtracted everything in A intersect B. And this stuff is in A intersect B, so it gets kind of subtracted once. And so similarly, this gets subtracted once. And so does this. What about the middle stuff? How many times is this counted now? Sorry, is it? Yeah, because everything in A intersect B intersects C. So okay, it was counted 3 times here, and then it was subtracted here because it's in A intersect B. It was subtracted here, and it's subtracted here. So it got added 3 times. It got subtracted 3 times. So now it's at 0. Which, okay, we're not done because we still have a 0 here. We haven't counted things the right number of times, but we're pretty close, right? Because all we have to do is fix this thing. Anyone have a suggestion how to fix it? Yeah, exactly. And now you can see that this gets counted once. Because it got counted 3 times, it got subtracted 3 times, and then it got added 1 more time. So in total, it's once. Okay. And that's like that description I just gave. I mean, it's maybe it doesn't feel like a rigorous proof, but that is like the proof of this. Okay, so these things tend to be kind of complicated, right? You have to, in order to figure out the size of the union of 3 sets, you have to work out 7 bits of information here. 7 things, but then yeah, you could just plug it into the formula. So you do have to like memorize this formula, basically. Any questions about this? Okay. Okay. Maybe let's do an example. Okay, so we've got 500 students. For some reason, I'm always doing students in this one today, but yeah, 500 students. Let's say that 50 of them enjoy running. Let's say that 60 enjoy Math 122. It's not a very realistic example. 30 enjoy skateboarding. And I need to give you more information. So let's say 10 enjoy running and skateboarding, or sorry, and Math 122. 12 enjoy, oh, sorry, I wanted this to be 30. I want to get the numbers right here because otherwise I'll have to actually do some computations. Sorry, 30 enjoy running in Math 122. 10 enjoy running and skateboarding. As you can see, these questions get really long. 12 enjoy Math 122 and skateboarding. And 3 enjoy all 3 of these activities. So how many students enjoy at least one of these 3 activities? Okay. Okay. Any suggestions? Yeah, just do that. Exactly. Like, let's say I let A be the set of students who like Math 122. B is the set of students that likes, oh, sorry, sorry. A is the set of students who like running. B like Math 122. C like skateboarding. And if it's asking how many enjoy at least one, it's asking you to compute A union B union C, the cardinality, and we can just write that down by inclusion-exclusion. So it should be 50 plus 60 plus 30, which is the size of A plus the size of B plus the size of C, minus, this is A intersect B, 30 minus 10 minus 12, and then plus 3. Okay, which I'm pretty sure I didn't compute, so I'll believe you. Yeah, so 91 sounds right. 110 plus, okay, these cancel. 188 plus 3, 91. Yep. Okay, so it is really that easy, you know. But the hard part is remembering this crazy formula. But any questions about that? Was that too fast? It's much faster to answer the question than it is to write the question. But yeah. Here's one thing. So suppose I didn't give you this information. Okay, that 3 people enjoy all 3. Okay, then you can't answer the question. But suppose I give you the information that A union B union C has size 91, and I ask you how many people enjoy all 3. Right? So if I erase this and I write the number that enjoy at least 1 is 91, and I ask you how many enjoy all of them, that's a question you can answer. Because, so I guess what I'm trying to say here is, so in an inclusion-exclusion question, so in this formula you have 8 things, right? You have this 1, 2, 3, 4, 5, 6, 7, 8 things. If I give you 7 of them, you can always find the last one. It doesn't matter which 7 I give you. So here I gave you these 7 pieces of information, A, B, C, intersection, 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 and the three-way intersection, and I asked you to find this. But if I gave you this, and these, and this, and that, and this, then and asked you to find this, you can do that just by changing, moving things around in the equation. So you could see variations of this question where you're given 7 of these pieces of information and you're asked to find the 8th, and it could be any of these things. So if you know 7 of these things, you can find the 8th, right? And it doesn't matter which 7. Also notice that you might be given information that's not really relevant. In this question, I told you there's 500 students. That didn't matter at all, right? So you don't necessarily have to use all the information that's given to you. However, if I asked you how many don't enjoy any of these things, then you take 500 minus 91, right? So anyway, there's all these different variations, but yeah. Any questions about that? Okay. Okay, maybe I'll do an example, one more example, using 2 sets where I give you different information. This will be a quick example. So suppose the size of A is 35, the size of B is 39, and the size of A union B is 60. So my question is, how large is A intersect B? Okay. Yeah. Yep. So, right, because we can write our formula again, right? Oh, actually, so it's going to be the other way around. So if you think about it, if I move this to the other side, move this to the other side, it'll be A plus B minus the union. But you can also just like plug in the numbers and then solve. So here I write 60. Here I write 35 plus 39 minus A intersect B. We solve for this. It's A intersect B is equal to 35 plus 39 minus 60, which is something like 74 minus 60, 14. That's what I got before anyway. Okay, so if I give you 3 of these pieces of information, you can always find the 4th. By the way, if you ever have time to actually check your answers for these things, you can always write a Venn diagram and see if it makes sense, right? So if I write 14 here, right? So let's say this is A and this is B. What number should I write here? So this is A minus B. Yep, 21, right? So because the total of A should be 35, there's 21 of them which are not in A intersect B. And then this should be 25, right? And to kind of check your answer, you can say, okay, if I write, so these are the correct numbers. A has the right size, B has the right size. The intersection is the answer that I wrote. And if I look at the union, it does add up to 60, right? 21 plus 14 plus 25 is 60. So we're happy. Okay, so this is just kind of a way to check your answer with a Venn diagram. Okay, any questions about this? Okay. So let me briefly mention something which is not really like super important for like getting marks in this course, but I think it's important for your general mathematical education. And this kind of goes back to something I briefly mentioned like the first day we talked about sets, which was that this whole thing about sets, it sounds really simple, but it's actually, it can get really confusing really quick. So let me ask you some reasonable questions about sets. Actually, the first one is a question that was asked weeks ago, the first time we talked about sets. It was asked by one of you guys, and it's a perfect question. So, I mean, it's a confusing question, but can a set contain itself as an element? So I should say there's probably not going to be any marks on tests about this, but it is kind of important to learn one day. So for example, could you have a set A which contains itself as an element? Like A is the set containing A. It's kind of like Inception, right? Yeah? Well, theoretically it feels like you could. And actually what I'm going to show eventually is that the answer to this better be no. Otherwise, horrible things happen in mathematics. So, but it does feel like if we just go with the naive definition of set theory we've constructed, that you know, a set is a thing that has elements. There's nothing to stop, if I just say a set has elements, there's nothing to stop you from doing this. But that's why that's only a naive, that's not the formal definition of set theory. But yeah, so there's nothing, it seems like this seems reasonable. Why not? So this is like but it's kind of like Inception, right? You know, the movie. So like A contains A, which contains A, which contains A. It kind of goes down forever in some sense, right? Well, and here's another reasonable question. So, you know, well, like, is there such a thing as the set of all sets? So sets of sets is okay, right? We've done lots of, like the power set, you know, and things like that. Sets of sets is okay. But can I take the set of all sets? Yeah? Ooh, yeah. So certainly if the answer to this is no, then the answer to this must be no, because this set would contain itself because it's a set. But so then it kind of boils down to, is this one no or not? But let's suppose we imagine that the answers to these things are yes, because, I mean, actually they both sound reasonable. Why not just take the set of all sets and all that? I mean, but then something bad happens. So this is something called Russell's paradox. So what if I let X be the set of all, let's say B, such that B is a set and B is not an element of B? Okay. Which, if the answers to these things are yes, then you can define this, because you could say, okay, take the set of all sets and then delete, or like take the set difference with the set of all sets that contain themselves as an element, and then you get all the sets that don't contain themselves as an element. This seems perfectly reasonable, right? I mean, if the answer to these things are yes, you can define this set. But now let me ask you a question. So true or false, you know, is X an element of X? Let's consider all the possibilities. So it's either true or false, right? Every statement has to be true or false. So suppose it's true. Okay. So what does it mean then? So X is in X. And what that means is that for x to be an element of x, that means x is a set and x is not an element of x. Right? So if I say x is so I'm supposing that x is an element of x, and this implies, by definition of x, that x is not an element of x. Because if x satisfies the condition that it's a set and it's not an element of itself, then it's not an element of itself. But that's a contradiction, right? You can't have both of these things true. So this is a contradiction. So what we should do is we should suppose it's false. So we suppose that x is not an element of x. But if x is not an element of x, then it satisfies the condition of being an element of x. Because if you look, x has the property, it's a set, and it's not an element of itself. So it satisfies the conditions. So it must be an element of x, which is again a contradiction. So basically, if we allow this to be a set, then all of mathematics breaks down, because the existence of this thing contradicts, no matter what you assume, it leads to a contradiction. So therefore, we have to basically assume that the answer, if we want set theory to make sense, we have to assume that both of these answers are no, basically. Okay, so